So, hello everyone. So, today we will start the ideal reactor operation, particularly we will be focusing only on continuous culture today. So, if you remember in the last lecture we discussed about the fed batch operation, where the intermittent feeding is done without any outlet, and we discussed continuous operation with free cells. So, today we are going to discuss continuous operation with immobilized cells, enzymes, and further continuous operation with cell recycle and continuous operation in series. So, before we go ahead, these are the outlines for today: the continuous operation with immobilized cells, with enzymes, with cell recycle, cascade chemostat, and then we will go for another continuous mode of operation, that is plug flow bioreactor. So, these are the schematic of batch. Fed batch are semi continuous and continuous. In the continuous, that is the CSTR as well as the PFR, and this biological agent can be free cell, free enzyme, immobilized cells as well as the immobilized enzymes. So, before we proceed, if you remember in the last lecture we were discussing CSTR with free cells. So, we will see couple of examples here. The first one is Zymomonas mobile cells are used for chemostat culture in 60 meter cube fermenter. So, volume is 60 meter cube. The feed contains 12 gram per liter of sucrose of glucose. So, SI is 12 gram per liter and Ks of organism is 0.2 gram per liter. Other parameters are given as mu max 0.3 hour inverse, Yx upon S is 0.06, Qp 3.4 hour inverse, and Ms is 2.2 gram per gram into hour. Now, the first question is, what flow rate is required for steady state substrate concentration of 1.5 gram per liter? So, the for part E, S is given as 1.5 gram per liter. So, what you need to find here is you need to find the D, or D is equals to mu equals mu max S Ks plus S. So, here S will be 1.5 gram per liter. So, we will get the value of D as 0.26 hour inverse, 6 hour inverse. Then we can find the what is the D. If you remember, dilution factor is F upon V. So, F equals to D into V. V is 60 meter cube, D is 0.26. So, we will be getting this flow rate as 15.6 meter cube per hour. Now, part B is, so this we got 15.6 meter cube per hour. At the flow rate of A, what is the cell density? So, here you have to calculate the cell density. So, if you remember the formula for the cell density, we can look at the overall material balance. It says D Si minus S equals D upon Y x upon S, Qp upon Y, P upon S plus ms into x. So, from here also one can find the value of x. Here ms is given, yp by s is not there. So, we can neglect this term. D is given, the only ms term will be extra. We will be getting the value of x as 0.42 gram per liter. So, we are getting x as 0.42 gram per liter. Now, part C, what is part C? The same flow rate, what is the concentration of ethanol? So, we need to find the P. The P equals, if you remember, P equals Pi plus Qp into x upon D. So, Pi we are assuming 0, so P becomes Qp. What is the value of Qp is 3.4 into x, we got 0.42 divided by D is 0.26. D is 0.26. So, we will get P as 5.5 gram per liter. So, we got P as 5.5 gram per liter. So, a 5 meter cube fermenter is operated continuously using a feed substrate concentration of 20 kg per meter cube. So, it means the SI value is, initial substrate concentration is 20 kg per meter cube. The microorganism cultivated in the reactor has following characteristics. So, it says mu max is 0.45 our inverse, Ks 0.8 kg per meter cube, Yx by S is 0.55. Now, the first part is what feed flow rate is required to achieve 90% substrate conversion. 90% substrate conversion means the S value will be 0.1 of SI, and that will be equals to 2 kg per meter cube, and volume given is 5 meter cube. Now, what is required? You require the flow rate. How will you get the value of flow rate? If you know the value of dilution factor, the dilution factor is defined as D as F upon V. So, if you know the value of dilution factor, we should be able to calculate the value of flow rate. So, for that, for part A we are going to calculate the value of D. So, D will be equals to mu max S upon Ks plus S, and its value is coming out to be 0.32 our inverse. And once D is known, what will be the flow rate? Flow rate equals to D into V, and that will be equals to 1.6 meter cube per hour. Now, part B, it says how does biomass productivity Qx at 90% substrate conversion compare with the maximum possible. So, how to get the maximum possible value? So, for that you need to first calculate what should be the D optimum, and how we calculate D optimum as mu max 1 minus under root Ks upon Ks plus Si, and in this way we will get the value of d optimum as 0.36 hour inverse. Now, after getting the value of d optimum, now we can calculate the biomass productivity, that is the Qx, which we can calculate using d optimum Si minus S. S is d optimum Ks upon mu max minus d optimum into y x upon s. So, we are going to get this value of Qx at optimum value as 3.33 kg per meter cube per hour. Now, how it is compared when d value is not d optimum? Then again we can quickly calculate what should be the Qx value at the value of d, which we calculated in the part A. In the part A, value of d was 0.32 hour inverse. So, in that case, if you calculate Qx at the given value of d, which was there in part A, it should be d Si minus d Ks upon mu max minus d into y x by s, and this value will coming out to be 3.17 kg per meter cube into hour. So, what does it mean at d optimum, how the productivity has increased from 3.17 to 3.33 kg per meter cube, and how much percentage it has increased, we can quickly calculate as 3.17 upon 3.33, and this is equals to 95% biomass productivity. So, earlier biomass productivity was 3.17, that is equals to 95% of the Qx optimum value. So, in this way we should be able to proceed with giving example in batch, fed batch and continuous culture. Now, going ahead, we will be now discussing chemostat with immobilized cells. So far we have discussed with the free cells, now we will go to the immobilized cells. So, let's see, there are free cells also and immobilized cells also. So, we will do this material balance for the immobilized cells. So, what it say, rate in is typically 0 because we are saying xi is 0. Rate of generation will be R xs into V plus Rx immobilized cell into V. So, there are two rate of generation plus out is F into xs, that is going out, consumption is 0 and this rate of accumulation at steady state it is also 0. So, what we are ending up with Rx is mu into xs, Rx immobilized is the same mu into x immobilized into effectiveness factor, total effectiveness factor is equal to F into xs. So, if we just divide F upon V as D, so it becomes D into xs, this becomes mu into xs plus eta t mu into x immobilized equals. Now, what is D here? In the case of D is mu 1 plus NT X immobilized divided by XS. So, if X immobilized is 0, then this becomes D is equal to mu, the chemostat with the free cells. Now, we will do the mass balance for substrate as well. What is coming in FSI, it is going out, coming in the rate of generations 0, there is no generation of substrate, going out Fs and rate of utilization. So, there will be RSV for the suspended cell and RS for the immobilized cell plus rate of accumulation, that term will also be 0 at steady state. So, now again this the same will continue here for the suspended cell, the RS will be mu upon y x upon s plus qp upon y p upon s plus ms whole into x. And what will be in the case of immobilized cell, the x will be replaced by effectiveness factor into x immobilized. The same is mentioned here. So, this becomes dSi minus s equals mu x upon s. For time being, we are neglecting these two terms plus xs into x immobilized. So, in this way we can again further rearrange here, D equals mu max s upon ks plus s, si upon s, it can be divided here. So, in this way you should be able to calculate the substrate concentration, or so if substrate concentration is given, you should be able to calculate the other parameter in this equation. Now, we can quickly compare the suspended cell. Here it says D equals mu, and immobilized cells where D equals mu plus the additional term is coming because of the immobilized cells. And how S is defined? S is dKs divided by mu max minus D, and here D, here the additional term of this immobilized cell is added here. Now, what we are seeing here is this dilution rate can be further enhanced as compared to the mu. Like if you just see the suspended cell, these are all the D critical where the substrate convergence becomes 0 because XIM is 0. And further, when we are increasing the XIM, what we are able to see here is we are able to operate as much higher value of the D critical. So, this is one strategy where chemostat is operated at D considerably high than D critical without washout. At given D, the presence of immobilized cell improve the substrate conversion and reduce the loss of substrate in the product stream. And further, this is important, this decreases conversion by the effect of mass transfer limitation, because once the cells are immobilized, they are going to experience the mass transfer resistance at the same time. So, the take home message here is the D can be greater than the D critical. Now, we will quickly go through the chemostat with enzyme systems. Continuous operation with enzyme will do the same mass balance rate in for the substrate, because this is enzyme. So, there will be no mass balance for the biomass, we will directly go with mass balance for the substrate. Rate in F into SI, rate of generation 0, rate going out F into S, rate of utilization is RSE, and what it will be RSE is, this is let us consider this following Michaelis-Menten constant. So, this will be V max S upon Km plus S into V. we are getting FSI equals Fs plus Rs into V, or you can say FSI minus Fs, or DSI minus S ds equals mu max S upon Ks plus S. So, this is very simple equation when you are having CSTR with free enzyme, and the moment you are involving the immobilized enzyme, the equation will remain same, only the term effectiveness factor will be added here, which comes due to the effectiveness factor of both external as well as internal mass transfer resistances. Now, next we are going to see CSTR with cell recycle. Now, what is important here is, if you want to improve the productivity further, so it is better to have more and more biomass. It means if you can have higher concentration of biomass, it can lead to the better bioprocessing. So, one option is, as we have seen in the continuous culture, some biomass is going out continuously. So, the strategy here is to recycle those biomass back here in the bioreactor. Basically, we are effectively utilizing the biomass. So, let us say if Xi is the biomass here, and so X is going out and XR is recycled. Similarly, if substrate concentration was Si here, so this is the S and this is the SR is the recycle, but here what we are saying, we are not doing anything with substrate recovery. The Si, whatever outlet substrate is there, that will be here equals to S and equals to SR. Further, we are not doing anything with the P, so whatever was the P, the same P will go. So, basically what we are doing here is, we are effectively able to separate the cell and recycle the cell. Now, there are two important terms you need to remember: the recycle ratio alpha, which is defined as FR, feed rate of recycle stream divided by F, flow rate of the feed. Second term, biomass conversion factor beta, this is defined as XR, biomass concentration in the recycle stream, divided by X1, biomass concentration which is going out of the bioreactors. Now, we will do the material balance on this part. So, it says what is the biomass in Fxi plus one more stream is coming here, Fr into Xr. So, only Xi is 0. So, only this term will be 0, this term will be there, plus rate of biomass generation Rx into V, going out F1 X1, and the rate of utilization per biomass is 0, and rate of accumulation at a steady state is 0 here. So, what we are getting here is Fr Xr plus Rx will be mu into X1 into V, plus F1 is, what is F1? F1 is F plus Fr, and what is alpha is the ratio of Fr upon F. So, F1 can be written as F under bracket 1 plus Fr will be, Fr is equal to alpha into F. So, 1 plus alpha. So, this becomes 1 plus alpha into F is equals to F1 into X1. Now, if you further simply rearrange it, so this term will be here mu, in fact X1 will be cancelled out in all three cases. So, what we are getting, F upon V will be dilution factor. So, we will get mu equals F upon V 1 plus alpha minus alpha into beta. So, in this way if you just see F upon V is D, so mu equal to D 1 plus alpha 1 minus beta. So, again when you are recycling the cell we are able to increase the value of D. So, we can operate the bioprocess at higher than this D critical. So, mu equals D 1 plus alpha 1 minus. So, what it says, typically value of beta is greater than 1. So, this value of alpha 1 plus beta will be less than 1. So, it says mu will be lesser than D. So, it says the chemostat can be operated dilution rate higher than that of the specific growth rate when cell recycle is used. And further, if you remember this mu equals my monad equation, mu equals mu max S upon Ks plus S. So, from here we can get the value of S, because the mu equals D 1 plus alpha 1 minus beta. If you put the value of mu here, so if you rearrange we are getting value of substrate as D k 1 plus alpha 1 minus beta plus mu max minus D 1 plus alpha 1 minus beta. So, it says what was the substrate concentration was D into Ks divided by mu max minus D. This was the substrate concentration with the free cell, but when we are going to do with recycle we are going to add one more term, that is 1 plus alpha 1 minus beta term. Now, we can do the similar mass balance for the substrate here. What is coming in FSI plus recycle stream FSR, what is going out F1 S1 plus rate of substrate utilization RS into V. So, we are saying FSI, FR will be, what is FR, alpha into F into S, F1 is 1 plus alpha into F into S, RS is, we are saying simply QS into X1, and this is the QS. It becomes FSI, you take this Fs this time, so alpha term will be cancelled out, it becomes FSI minus F or F upon VSI minus S, it will be simply D SI minus S, this equals to rate of substrate conversion into X1 into V. So, in this way we can find the value of X1 as D SI minus S divided by mu upon Y X upon X plus QP upon YP upon S plus MS. So, in this way if we can neglect the term this product formation and maintenance term, then we will end up with D SI minus S divided by mu upon Y X upon S. So, Y X upon S will go in the numerator, so it become Y X upon S, SI minus S into D, and mu equals to D 1 plus alpha 1 minus beta. So, further this D can also be cancelled out. So, it becomes Xi as X upon S, Si minus S divided by, so this is the additional term we are getting in the biomass concentration. Now, we can see the biomass productivity in the chemo scale with recycle. This is the expression of substrate we have derived, and this is the this x1 we have recently we discussed in the last slide. Now, volumetric flow rate of biomass Qx is d into x1. So, we can simply multiply the d here. So, d is multiplied here. So, this becomes volumetric biomass productivity, and this was volumetric biomass productivity without cell recycle. So, you can compare these two expressions. Now, if you just see interestingly, this is the dilution rate versus Qx or steady state cell concentration. So, what was the biomass? Biomass was almost constant, then at the D critical the biomass suddenly becoming 0, but we are having CSTR with recycle, we are able to extend this D optimum to a different value. It continues increasing, then further it decreases. So, this let us say becomes D critical recycle is much higher than the D critical without recycle. In the similar way, if you just see the Qx recycle, what is the concentration of X with recycle, it is much higher than the Qx without recycle, and similarly this biomass concentration is also higher with the recycle. So, these are the this salient advantage of CSTR with the cell recycle, and it is very easy because the cell is anyway going to the outlet stream. It is better to recycle and reuse it. Now, further there is a possibility that we can have the cascade system where this you can have two CSTR in the series. So, this outlet of one becomes this inlet of this other bioreactor. So, let us say if the concentration was here xi, this will be x1 and this will be x2. So, this allows separation of growth and product stages. So, we can design in such a way that in one case our objective is the biomass, we are getting more and more biomass, and in the second stage our objective can be getting more and more product. Second option is if you want to having two optimum condition, one is having different temperature pH and second is having different temperature pH. So, we can have two different reactors. So, in one case we can optimize this temperature, one set of temperature and pH. In this bioreactor we can optimize different set of temperature and pH. So, it gives a better control of substrate concentration, but it requires individual monitoring per stage, and once you are able to use in the series, so it reduces the reactor volume for the same conversion. Typically for this recombinant protein production, this cascade chemostat system is used. Now, what we have discussed so far is we have discussed the batch, we have discussed the fed batch, and in the continuous we have discussed the continuous state tank reactor. Now, in the continuous we are going to discuss one more bioreactor, that is the plug flow bioreactor. Continuous operation in plug flow bioreactor. So, here again we will quickly see with the free enzyme, immobilized enzyme, free cell and immobilized cells. So, what is plug flow bioreactor? The plug flow bioreactor is a type of chemical reactor where reactant flow in one direction as a plug. That is why we are saying it a plug flow with no back mixing. So, each infinitesimal element of the fluid has a different residence time and allowing for the high conversion efficiency. So, what is the working principle for this PFR? The reactants enter to the reactor and flow through a discrete plugs, and each plug reacts as it moves along with the reactor length. So, here the particularly the dependent variable is considered as a length in place of time, and conversion increases with the reactor length, and as this is a plug flow, so there is no mixing in the axial direction. I have listed a couple of examples where this PFR are being exploited, that is the petrochemical processing, polymerization reactions, pharmaceutical manufacturing, as well as waste treatment and environmental engineering. So, as I told, in the plug flow reactor, the volume will be A into delta Z, because the reaction is completing with increase in the height or with increase in the Z. So, let us say F is the volumetric flow rate, A is the tube cross sectional area, RS is the enzymatic rate of reaction, and superficial velocity will be defined as U equals F upon A. So, what we are going to do, we will be doing the mass balance only at this delta Z first, and then further we will integrate it to get for the entire length of the PFR. So, let us say in FS, what is coming here is FS as Z. What is the generation for substrate? 0. What is going out? Fs Z plus delta Z. Rs into volume is A into delta Z plus rate of accumulation is 0, because it is operating as steady state. So, if you just rearrange it, becomes Fs Z minus Fs Z plus delta Z equals mu max V max S upon Km plus S into A into dz. So, we can quickly rearrange it. So, this term becomes ds, and if you take out this d delta z here, so this term becomes f upon a ds upon dz, and what is f upon a is the velocity u, velocity u. So, it becomes u into ds upon dz. This equals to the minus V max S upon Km plus S. So, it becomes U into ds upon dz equals minus V max S upon Km plus S. So, we can quickly integrate, because this is very simple. This will be Km upon S plus 1. So, if you integrate, you will be having this Km upon S will be ln Si upon S, and this 1 will be integration of delta S means Si upon S, both will be divided by V max, will go to the other side, and U will be also, and this side will get the Z, or we are getting the Z as the L. So, we are integrating 0 to L. So, in this we can find what is the typical length, and what is the residence time. Tau is defined as V upon F. V is area into length, and flow rate is area into velocity. So, A can be considered out length upon velocity. So, this can be further, length is there, if you divide with this velocity, it becomes the residence time. Tau is 1 upon V max Km Si minus Sf plus Si minus Km Si upon Sf plus Si minus Sf. So, this enables us to calculate the length of reactor as well as the residence time required to achieve a specific conversion at a particular flow rate for an enzyme reactor. And expression is similar to the batch reactor. In both S and P vary continuously during the reaction period, and in the PFR those changing continuously as improving movements from the inlet to outlet, because this is how the reaction is taking place, and it is completing as it moves along the reactor length. Now, similar to this pre-enzyme, one can have the immobilized enzyme. So, only change you need to make is multiply with the effectiveness factor, and after doing multiplying it is not easy to integrate as effectiveness factor as a function of S. So, for this there are different special bioreactors which are utilized for PFR with immobilized cell. One example is the packed bed bioreactor. So, in the real situation, packing in the packed bed can because back mixing and therefore axial dispersion of the liquid is taking place. So, the design equation need to be modified because here we don't, there is no possibility of axial dispersion or mixing. Next, we can quickly go through this PFR with free cells. So, what is going to change? There was the R enzyme and this will be the Rx, and V is the A into delta Z, rate of accumulation is 0. So, this becomes F dx upon dz. So, we will be getting F, or if you divide F upon A, it will be U dx upon dz is equal to Rx, and Rx is equal to mu into x. So, in this way we got the final equation U into dx upon dz equals mu into x, and this again mu will be written as mu max S upon Ks plus S, and if you integrate it, dx upon x will be ln xf upon x plus 1 upon mu max, if you assume mu equals to mu max, that is it. In the similar way, we can do mass balance for the substrate in FSZ, generation 0, going out this, and rate of utilization Rs into V, velocity volume is A into delta Z. So, this becomes U into ds upon dz equals minus Rs. And what is the rate of substrate utilization? This mu upon yx upon x plus qp upon yp upon s plus ms into x, and this. So, in this way we should be able to calculate the biomass balance and the substrate balance for the plug flow bioreactor. So, there are certain limitations, it requires the continuous supply of inoculum because whatever is going in, it is going out, there is no lateral mixing. So, what is the solution? The immobilized cell in the reactor, or we can go with the packed bed. So, somehow we have to immobilize the cells if you do not want to continuous supply of inoculum. Now, here we can see how the substrate profile changes with Si to Sf and what is the volume of the reactor. So, if you compare if you see quickly, PFR is more efficient than a single stage CSR. This is the let us single stage CSR to achieve high conversion with less volume. So, when volume is less, the PFR, this is giving much higher efficiency at the low volume, but as we are increasing the volume, so there becomes, if you just see, then multiple CSTR in series approaches the performance of plug flow bioreactor. This is dotted line, almost it is reaching to the dotted line when you are having this multiple CSTR. Then other option is you can have the combination of reactor like CSTR followed by the PFR. It can be used to optimize the performance, depending on the kinetics and economics. So, in this way we have seen the comparison of batch, plug flow bioreactor and the CSTR. So, in practice typically this batch processing is preferred to PFR for enzyme reaction because of operating condition. We are having the continuous supply of oxygen here. I will stop here. So, today we have summarized this chemostat with free cells that was discussed in the last lecture. We continued with the immobilized cells, chemostat with the enzyme, chemostat with the cell recycle and further cascade chemostat. Then followed by that we saw another continuous mode of operation, that is the plug flow bioreactor, and that we have seen in this case of plug flow bioreactor, the conversion is completing by increasing the length. So, here we need to calculate what is the length of bioreactor rather than the time as a dependent variable. Thank you so much.